Section 2.1, Radical Functions and Transformation. This section focuses on investigating the function y equals root x using a table of values and a graph. We're then going to look at graphing radical functions using transformations and identifying the domain and range. A radical function is a function that involves a radical with a variable under the radicand. So the base function would be y equals the absolute value of x. You can create graphs of radical functions by using tables of values or technology, or by transforming the base radical function. The effects of changing the parameters in radical functions are the same as the effects of changing parameters in other types of functions. So first of all, we need to discover what that base function of y equals root x actually looks like. So we're going to start by graphing y equals root x. To do that, we can pick values for x to substitute in. We want to be careful when we're picking values so that we can actually take the square root of them. So that means that we can't have anything that's a negative, because we can't take the square root of a negative number. So if I put in 0, the square root of 0 is 0. And so the first point on my graph is the point 0, 0. If I substitute in x equals 1, the square root is 1. I'm going to move this axis over a little bit so that it actually lines up where it's supposed to, and let's regraph 0, 0. So 1, 1 will be here. I wouldn't want to use the square root of 2 because 2 is not a perfect square. So let's jump up to 4. If x is 4, the square root of 4 is 2. The next perfect square is 9. The square root of 9 is 3. So we're going to go over 9 and up 3. The next perfect square is 16. The square root of 16 is 4. And I'm going to stop there because that's all of the room that I have on my graph. I've got something not quite right here. Oh no, there we go. Should have an arrow on the end because it will continue in that direction. We just stopped because our graph ran out of room. So let's look at the domain and the range. The domain for the absolute value of x is that x has to be a positive number. So that means that it can go from 0 to positive infinity. Remember that 0 is included, so it gets a square bracket, and infinity always has a round bracket. The range for this graph, the lowest point on my graph is again 0, and eventually that arm will continue to raise up to positive infinity. So again, it's 0 to infinity. Let's look at our next graph, y equals root x minus 2. So if we're doing y equals root x minus 2, let's start with a table of values. Remember that from the previous graph, we could graph root x as 0, 0, 1, 1, 4, 2, and 9, 3 would be all that I would have room for this time. So those key points and then I can make up a mapping for y equals root x minus 2. That 2 is inside the function because it's under the square root sign. That means that it's going to affect x, and it's going to do the opposite. So we are going to add 2. There is nothing in this function that's going to affect the y value. So we're going to add 2 to each of our x values and leave the y one unchanged. So we end up with 2 and 0, 3 and 1, 6 and 2, and 11 and 3. Graphing that function, 2 and 0, 3 and 1, 6 and 2, and 11 and 3 would be out here. So I quickly run out of room on my graph because that graph has been shifted to the right. The domain of this new function now goes from the x values start at positive 2 and go to infinity. The range still starts at 0 and increases to positive infinity. Let's graph this next one on the same graph. I'll just use a different color. So again, those same key points from our base function of y equals root x. So 0, 0, 1, 1, 4, 2, 9, 3. This time, when we do our transformation, the 3 is outside of the square root. That means that it's going to affect the y value. So the x value stays the same, but our y values we're going to subtract 3 from. So if we subtract 3 from each of our y values, we end up with 0, negative 3, 1, negative 2, 4, negative 1, and 9, 0. Let's graph those. 0, negative 3, 1, negative 2, 4, negative 1, 9, 0. And so our graph is now this green function. So what's happened from the original blue graph is that graph has all been shifted down 3 units. So our domain this time is back to being from 0 to positive infinity. The range is going to go from this time negative 3 is the low point, and eventually it will increase to positive infinity. Sketch the graph of each function using transformations. Compare the domain and range to y equals root x and identify any changes. So again, let's do a quick sketch of root x because we need to practice graphing that. So when x is 0, y is 0. If x is 1, y is 1. If x is 4, the square root of 4 is 2. And the square root of 9 is 3. So there's that base function. Writing out our key points, 0, 0, 1, 1, 4, 2, 9, 3. Now, let's make a mapping diagram to see what transformations take place. So when we're looking at that mapping diagram, the first number that we come across is a 3. That's outside of the square root sign. That means that it's going to affect y, so we're going to end up with 3y. The negative is inside of the root sign, so it's going to affect x. And this negative 1 is inside the function, so it's going to affect x, but do the opposite. So we're going to add 1 to each of our x values. Means that our new points become 1 and 0, 0 and 3, negative 3, 6, and negative 8, 9. Let's graph those. So 1 and 0, 0 and 3, negative 3, 6, and negative 8, 9. And so our graph this time looks like this. So let's compare the domain and range. If we look at our original function, and we'll do it color-coded, so the domain for the original function goes from 0 to positive infinity. The range also goes from 0 to positive infinity. With our new transformed function, the domain this time starts to the left, it will go all the way to negative infinity is the lowest point. The highest x value is going to be positive 1. And that's due to that reflection or that negative out front of the x. The range, the lowest point is 0. The highest point is infinity. Here's another one. Y minus 3 equals negative root 2x. So the first thing that we want to do is we want to rewrite this in the form that we're used to. So we're going to add 3 to both sides. We end up with y equals negative root 2x, and that plus 3 is outside of that function. So again, base function is root x, so 0, 0, 1, 1, 4, 2, 9, 3. There's the base function. Make a list of those key points. And now let's look at our mapping for this newly transformed function. So the first thing that we have is this negative out front. It's not under the root sign, so that means it's outside of the root x base function, so it's going to affect y. The 2 is inside the function, so it's going to affect x, and it's going to do the opposite, so we're going to divide each of our x values by 2. The 3 is outside the base function, so it affects y, and we're going to add 3. When we transform each of those points, then we end up with 0 and 3, 1/2 and 2, 2 and 1, and 4.5 and 0. Let's graph those. 0 and 3, 1/2 and 2, 2 and 1, and 4.5 and 0. And so our graph now looks something like this. Let's look at our new domain and range. The domain for our new function, so the x values go from 0 to positive infinity. The range has a maximum point this time. The minimum is going to be at negative infinity, but the maximum value for y is going to be positive 3. Last example. Mayleen is designing a symmetrical pattern. She sketches the curve shown and wants to determine its equation and the equation of its reflection in each quadrant. The graph is a transformation of the graph y equals root x. What are the equations of the 4 function Mayleen needs to work with? So let's start by figuring out what this transformation actually is. So it's a transformation of y equals root x. So let's graph root x on our graph. 0, 0, 1, 1, 4, 2, and I can't show the 9 and 3. So to figure out what that transformation is, we want to look at what happens to each of the x, y's to produce our new function. Because the point 0, 0 is in both graphs, it hasn't been, it's kind of the start of our graph, it hasn't been moved, means that we're not adding or subtracting anything to the y values. That means that the blue graph is formed by a transformation of y, by a stretch of y equals root x. So if we look at the distance here versus the distance to here, we can see that it's twice as tall. That means that we took our y values and we multiplied them by 2. If we're multiplying the y values by 2, that means that our new equation, that 2 has to be outside of the base function root x. So that gives me the graph of, or the equation of the graph in quadrant 1. Now let's look over here in quadrant number 2. In quadrant number 2, in order to get that same graph, we would have to reflect it in the y-axis, or about the y-axis. That means that our x values are going to become negative. So in this base function, then we would end up with negative x. Let's skip and do quadrant 4. So quadrant 4 is down here. Quadrant 4 could be found by doing a reflection of our function in the x-axis. So that means that the y values are going to become negative. And so we can write that as taking the negative of the whole function, so negative 2 root x. Quadrant number 3 is down here. And so what we need to do is we need to take our graph from either quadrant 2 or quadrant 4 and reflect them again. So let's start with our graph in quadrant number 4, which is our last equation. If we're going to reflect that equation about the y-axis, it means that we also want to make the x value negative. So we end up with y equals negative 2 root negative x.